Good day to everyone. We are here to present our design project entitled Design of a Sustainable Refrigerated Tracking System for Optimized Meat Transport. I am Miguel Leandro Hoson, and with me here today is Ms. Claudine Alvarez, Mr. John Jeremy Batas, Ms. Crystalline Enrinal, Ms. Gladys May Guida, Mr. Aldrin Malabanan, and Ms. Tricia Ann Manalo.
Meat is highly perishable and requires consistent cooling during transport to ensure safety and quality. Our project focuses on designing a sustainable refrigerated tracking system by evaluating key refrigeration technologies or vapor compression, absorption, and thermoelectric. We prioritize vapor compression for its proven alternatives for off-grid and eco-friendly use. Addressing issues like refrigerant leakage and temperature loss, our goal is to find a reliable, energy-efficient solution that minimizes environmental impact and reduces meat spoilage in transit. Refrigeration plays a critical role in food industry, especially for preserving during transport. But as demand grows, so do environmental and economic concerns, mainly from high energy use and harmful emissions. Traditional diesel-powered systems and high GWP refrigerants have worsened the problem. In response, the industry is now shifting to low GWP refrigerants like R32 and R290 and adopting technologies like variable speed compressors and smart monitoring systems. Our study supports this transition by proposing a sustainable refrigerated tracking system that boosts efficiency, cuts emissions, and aligns with global sustainability goals.
To develop an effective refrigeration system for meat transport, we started by identifying the core thermodynamic principles. The system follows the reverse Carnot cycle, which serves as the ideal model for cooling process. While real systems are never perfectly efficient, this principle helps guide design decisions. We measure system performance using the coefficient of performance, or COP, which compares the amount of heat removed to the work input. Our goal was to improve both energy efficiency and temperature stability, critical factors for preserving meat during transport. Next. Next is we considered key design influences. The refrigeration systems must be capable of maintaining the proper temperature range between -1 degree Celsius and 4 degrees Celsius, regardless of the type and quantity of meat. At the same time, it must account for various sources of heat gain, including insulation limitations, air exchange during door openings, and environmental exposure like solar radiation. Choosing a refrigerant such as R290, which has a low global warming potential, also contributes to both system performance and environmental responsibility. Next, our approach combines simulation and experimental validation using MATLAB and Engineering Equation Solver (EES). We simulated the refrigeration cycle under different refrigerants and varying conditions. We examined how different compressor efficiencies, insulation quantities, and ambient temperatures would affect overall performance. These simulations help us identify system configurations that required the least refrigerant charge, offered the highest COP, and showed the lowest temperature fluctuations even under potential leak scenarios. Next, to support our simulations, we conducted experimental testings through a laboratory setup that simulates actual transport conditions. This includes baseline performance tests with standard and alternative refrigerants, as well as controlled leak simulations to monitor how the system reacts to refrigerant loss. We monitored key parameters like internal chamber temperature, power consumption, and refrigerant pressure to validate the simulation data. Finally, next, we conducted a comparative analysis across different systems and refrigerants. We assessed each options based on four main criteria: energy efficiency through COP, temperature stability, environmental impact, and cost effectiveness. The goal was to identify the most efficient and sustainable solution for meat transport, one that minimizes refrigerant use, resists leaks, and maintains strong thermal insulation.
Technical matters of importance. We have three types: rotary compressors, screw compressor, and reciprocating compressors. Rotary compressors, they employ a rotating impeller to draw in refrigerant vapor and compress it. These are compact, relatively quiet, and fit into small refrigeration system such as those in home and small commercial uses. Screw compressors. They employ two intermeshing screw for compressing the refrigerant vapor. They are highly reliable and efficient, so they can be used in large refrigeration system and such those that are used in industrial steps and refrigerated vehicle. We also have reciprocating compressors. These compressors are refrigerant vapor by employing a piston. They are strong and low price but noisy and less efficient compared to others. We also have factor influencing selection. We have efficiency ratings, cooling and capacity, operating condition, noise level, and cost. Efficiency ratings. Compressor efficiency is rated with the use of coefficient of performance or COP, which is relation of cooling ability and power input. High COPs reflect increased efficiency. The cooling capacity, the compressor size and type control the cooling capacity of the system. While in operation condition, application needs, refrigerant type, and ambient temperature dictates the compressor choice. Noise level requirement are consideration in residential and certain commercial application. Lastly, we have cost. Initial cost and maintenance cost over a long period are to be taken into consideration. Next slide po. Evaporators. The evaporator takes heat from the refrigerated area and evaporates the refrigerant. Major design consideration are surface area, material selection, fine design. In surface area, more surface area means high efficiency in heat transfer. In material selection, copper and aluminum are frequently used materials because of their high thermal conductivity. Fins add surface area and enhance heat transfer. Condenser. The condenser shed heat from the refrigerant, allowing it to condense back into liquid form. This design factor includes surface area, material selection, airflow. In surface area, increased surface area are favor heat dissipation. Copper and aluminum are regularly used as the materials for a condenser. Airflow. Proper airflow around the condenser is required in order to dissipate heat optimally. Next slide po, please. Control system. We have four. Role of control system. Control system control the running of the refrigeration system in order to provide maximum performance, ensuring temperature constancy and minimize energy expenditure. B. Programmable thermostats. These permit user to select preferred temperature and manage the functioning of the system. Smart sensors. The sensors are used to sense the different parameters such as temperature, pressure, and airflow and transmit data to the control system. Automated feedback system. This system make use of sensor data to change the compressor, speed, refrigerant flow, and other parameters in order to maintain optimum performance and energy efficiency.
Energy efficiency standards. For letter A, we have ARI, or Air Conditioning, Heating, and Refrigeration Institute. ARI issues standards and certification for refrigeration equipment, including compressors, heat exchangers, and full systems. ARI certification guarantees that products comply with certain performance and efficiency standards. B, we have the ISO, or the International Organization for Standardization. ISO 5149 sets standards for the performance and safety of refrigeration systems, including requirements for refrigerant charge, leak detection, and energy efficiency. Next slide.
Let's now talk about the assumptions and justifications. For the assumptions, the study assumes that refrigerant properties remain constant within typical operating conditions, simplifying thermodynamic modeling. Heat transfer in system components is analyzed under ideal conditions with negligible internal losses. Standardized environmental settings, which is 30 degrees Celsius and 60% humidity, and consistent cargo loads allow for fair performance comparisons. The system is evaluated under steady-state conditions, avoiding the need for dynamic modeling. Minor refrigerant leakage is considered insignificant for short tests, and internal temperature distribution in the cargo area is assumed uniform, simplifying control system design. Next slide po. For the justifications, the assumption used in the refrigeration system model, such as constant refrigerant properties, minimal heat loss, standardized testing conditions, steady-state operation, and uniform temperature distribution, are largely justified by existing research and technical standards. Studies confirm that refrigerants behave predictably within operating ranges. Modern insulation reduces heat loss effectively, and consistent test conditions allow reliable performance comparison. While the uniform temperature assumption is supported for initial modeling, research shows actual temperature varies due to cargo layout and airflow, necessitating future monitoring improvements. Limitations of these assumptions, including overlooked inefficiencies and localized risks, are acknowledged. Sensitivity analysis and dynamic modeling are planned to refine system accuracy and maintain real-world relevance. Next slide po.
Now proceed to possible sources of errors. Number one is measurement errors. Measurement errors in refrigeration system for meat transport trucks can compromise sensor reliability and overall system performance. A key issue is improper sensor calibration, which can cause inaccurate temperature or pressure readings, potentially missing signs of refrigerant leakage and leading to spoilage. Environmental factors such as external temperatures fluctuations, track vibrations, and altitude changes can also distort sensor data. For instance, sensors near doors may pick up false readings during loading, and pressure sensors might misread due to elevation shifts. Number two is modeling errors. Simulations are crucial in refrigeration system design as they help predict performance under various conditions. However, they often rely on simplified models with ideal assumptions that may not reflect real-world scenarios. This can lead to overlooking issues like refrigerant leaks or overestimating system efficiency. Additionally, simulations may fail to capture dynamic behaviors such as frequent door openings or the thermal inertia of cargo, which significantly affect temperature distribution and system performance in practice. Next slide po. And number three, external factors. External factors like ambient temperature, humidity, and load variation significantly affect refrigeration system performance and can mask signs of refrigerant leakage. Temperature fluctuation across different climates and high humidity can alter system efficiency, while frost buildup and varying cargo loads, along with frequent door openings, can mimic symptoms of a leak, making detection more challenging. For mitigation strategies to minimize errors and challenges in designing a refrigerated meat transport system, a thorough mitigation strategy is needed. This includes using reliable, high-precision sensor resistant to environmental disturbance and conducting controlled experimental tests, simulating various operational scenarios. These measures help optimize system performance, and improve understanding of its behavior under different conditions. Next slide.
For the design data comprises all the variables necessary to establish the requirements for the design of a refrigerated trucking system. The parameters that are needed to determine the cooling load include the transmission load, the internal heat generated by occupants, heat produced by the equipment, the infiltration load from outside air, and the system's refrigerating capacity. Next slide. Table 2 shows the proposed refrigerated tracking system's dimensions. Next slide, 2. And Table 3 presents also the working parameters of the refrigerated tracking system. Next slide. And here we have is the design of the proposed refrigerated tracking system.
Design option 1, vapor compression cycle. This option uses separate vapor compression system for the pre-cooling and storage room, each with own compressor, condenser, evaporator, and expansion valve. Ammonia is compressed, condensed, and expand, and evaporated in a 4-phase cycle to absorb heat from the cold room. It exhales in the evaporator as saturated vapor, then gets superheated before returning to the compressor.
So design option 2 vapor compression cycle with heat exchanger. This design adds a heat exchanger to improve efficiency. After compression and condensation, the refrigerant is subcooled in a heat exchanger before expansion. It then evaporates to cool a storage area and returns through the heat exchanger for superheating. This enhances cooling capacity, reduces compressor risk, and improves reliability ideal for meat transport.
Design option 3 or the two-stage vapor compression cycle with heat exchanger. This advanced system uses two cycles, low stage or the R404A and high stage R134A, linked by a cascade heat exchanger. It improves efficiency and supports ultra-low temperatures needed for meat preservation. Benefits include better refrigerant matching, reduced pressure, oil separation, and easier maintenance.
For the design selection criteria, first we have the work of the compressor. A compressor compresses the refrigerant to produce a high pressure, high temperature gas. It is essential to the operation of a refrigerator because it circulates refrigerant throughout the refrigeration system. The refrigerator compressor is a motor and a pump that compresses the low temperature, low pressure refrigerant gas that comes from the evaporator. A refrigerator compressor interacts directly with the condenser, evaporator coil, and expansion valve. The compressor's performance has a direct impact on the overall energy consumption, cooling capacity, and system reliability. Therefore, choosing the appropriate compressor type and configuration is an important aspect of determining the most effective refrigeration design. Second, refrigerating capacity. It is a crucial factor in ensuring the proper functioning of a refrigeration system. It determines the rate at which heat can be extracted from the refrigerated room while keeping it at the right temperature. An improperly sized refrigerated system with either insufficient or excessive capacity can result in inefficient operation, increased energy use, and poor product preservation. A higher refrigerating capacity enables the facility to store a greater quantity of meat. Therefore, refrigerating capacity will be a key criterion when comparing the different design options. Next slide po. Third is the coefficient of performance. It is a key measure of the refrigeration system's efficiency, representing the ratio of the cooling effect produced to the electrical power consumed by the compressor. A higher COP indicates a more efficient system that delivers greater cooling capacity for less energy input. When evaluating different design options, the COP serves as a critical criterion because it directly impacts operational costs and energy consumption. Selecting a design with a higher COP not only reduces electricity usage but also lowers environmental impact, making it an essential factor in optimizing the truck refrigeration system's performance. Lastly is the cooling load. The cooling load refers to the total amount of heat that the truck refrigeration system must remove to maintain the desired temperature inside the cargo area. This load is primarily influenced by heat transfer through the truck's insulated walls, floor, and ceiling, which depends on the type and thickness of insulation used. External factors such as solar radiation, ambient temperature, and road conditions also contribute to the heat gain, particularly through areas like the rear door. Additionally, the thermal energy from the stored product itself adds to the cooling load as the system must keep the product at the required temperature. Air infiltration through door openings and any internal heat sources, such as lighting or equipment, further increases the load.
For the summary of the design selection criteria, for the cooling load, design option 2 is the best choice because it required a cooling load of 1.9876 kilowatts, accounting for heat gain from insulation product heat and air infiltration. For the compressor work, the system requires a total compressor work of 5.9748, and an efficient compression ensures reliable refrigerant circulation and influences energy consumption and performance. Next slide. For the coefficient of performance, the calculated COP is equal to 0.3357. The system demonstrates moderate efficiency. For the refrigerating capacity, the design achieves a refrigerating capacity of 1.9894 kilowatts, sufficient to preserve the meat at negative 35 degrees Celsius. As a conclusion, design option 2 provides a balance of thermal performance and system protection. Though its COP is lower, the enhanced heat exchanger increases effectiveness, ensuring stable operation for refrigerated meat transport.
For our final design selection, we chose design option 2 based on its overall balance between performance, energy use, and reliability. This system effectively meets the required cooling load of 1.9876 kilowatts. It accounts for heat gain from multiple sources, including insulation, the heat from the stored meat, and the air infiltration. The inclusion of a heat exchanger improves thermal regulation and helps reduce the overall impact of heat entering the system. In terms of power requirements, the system needs a total compressor work of 5.9748 kilowatts. This is divided into two stages, 1.4718 kilowatts for the low stage and 4.5066 kilowatts for the high stage. While this does indicate a significant energy input, it ensures that the refrigerant is circulated effectively, contributing to the system's reliability. The system's coefficient of performance is calculated at 0.3357, which may seem lower than ideal. However, the design compensates for this through the inclusion of a heat exchanger. This feature enhances both subcooling and superheating process, helping to optimize thermal performance even with the moderate energy efficiency. The refrigerating capacity achieved is 1.9894 kilowatts, which is sufficient to preserve meat at a target temperature of negative 35 degrees. This accurate sizing helps avoid both undercooling and overcooling, making the system more energy efficient while protecting product quality. In conclusion, design option 2 strikes a practical balance between thermal performance and system protection. Although its COP is not the highest, the design improvements, particularly the use of heat exchanger, allow for better temperature control and operational stability, which are crucial for reliable and sustainable meat transportation.
For the implementation of our sustainable refrigerated tracking system, we chose design option B due to its reliable performance and cost effectiveness. The total project cost is 293,000 pesos, which includes all the major components needed for the system to function efficiently.
For the economic analysis, evaluating the system's depreciation expenses enables the researchers to determine the financial attractiveness of the equipment for potential future investments. Additionally, it provides an insight into the machine's overall economic viability. Next slide. A typical commercially used vehicle has a useful life of 8 years. By the end of this period, it has a salvage value of 30% from its original cost. Using the formula of depreciation, which is first cost minus salvage value over useful life, we can get the depreciation value of the truck, which is, next slide. So 25,637.50 pesos. In conclusion, the proposed design for the refrigerated tracking system has a yearly depreciation value of 25,637.50 pesos. Next slide.
The conclusion. The study compared the refrigeration system for optimal transport of perishable goods in refrigerated truck. The vapor compression system with a heat exchanger was found to be the most efficient and stable, especially for meat transportation. It minimized refrigerant charge, enhanced energy efficiency, and reduced product spoilage. The study also highlighted the importance of establishing the cool load considering ambient temperature, solar radiation, insulation, and cargo-generated heat. Despite simulation and modeling limitation, The findings are useful for designing efficient and sustainable refrigerated tracking system. The sustainability focus is evident through the use of low GWP refrigerant, energy efficient parts, and LOT technology integrated for better monitoring and maintenance. The study contributes to make refrigerated transportation system more sustainable and efficient.
Recommendations. Design option 2 a vapor compression refrigeration system with a heat exchanger is the recommended solution for transporting perishable meat products. By subcooling the liquid refrigerant before expansion and superheating the vapor before compression, this design enhances heat absorption and compressor efficiency. Ensuring stable low temperature is essential for preserving meat quality and preventing spoilage. Compared to the basic compression system option 1, option 2 delivers superior energy efficiency and better compressor protection with only a moderate increase in cost. While design option 3, a two-stage system with heat exchanger, offers the highest efficiency and lowest temperature, its added complexity and significantly higher initial cost make it less practical for most meat transportation needs. To conclude, design option 2 balances high performance, cost effectiveness, and environmental responsibility and operational reliability, making it the most practical and sustainable choice for refrigerated meat transport. And that is the presentation of Group 4. And we thank you for listening.